Good day, everybody, and this is Geogebra Lecture 5, and today we'll discuss rather about some leftover functions which I'll do first, and then what next after you plot a function. So functions continued function, continue with function, that is what we will be doing, and what are the derivative of a function, that also I will tell. Okay, and so let us start from the function itself as usual. So come to this, and as usual I prefer this mode of GeoGebra because simple syntax typing will give you a result directly, and it will be very fast to work in this mode. So start calculator mode, and then you once you go there, you write the function we have seen. Now today first I begin with another interesting function, interesting as well as important functions, like say I write a function sine of ax then divided by x. This is a function, okay, and it looks like a sine wave, but its amplitude really get damped out, not by any exponential function, by x itself. It happens like that because of the fact, and at x equal to 0, as you can see, numerator is 0 and denominator 2 is 0. Therefore 0 by 0, in the limit it will become equal to 1. Those who know limits, they can easily figure it out, because 0 by 0, take the derivative of the numerator, it is cosine x, and take the derivative of x, it is 1. Therefore it is 1. Okay, so and to make it slightly more amplitude wise, I will just change this curve in this fashion: f of sine x divided by x. So the same nature of curve, only thing all the y coordinates are amplified by a factor of 5, and this curve looks like that. Okay, and this curve, this function is very much useful in signal processing. Anyway, let us not go into that, but as a first look, this is a very nice looking curve, and the description of the function is this, and if you return, it will become a function of this kind, and it is like this. I am rather slightly tempted to play with this function. For example, I want to change the dimension here by a factor, say a. I'm so sorry. You bring it down here in the forward, then write a and do like this. So it is asking for creating a slider, because we know the amplitude I would like to vary, so it has created a slider of this kind, and your curve is like this. Slider initial value is set to 1, And as you can see, as you vary the value of a, the shape of the function is going to change like that. Okay, this is the thing. And next thing, this I want, this is a review thing, but this is a very nice looking function, so I will do that so that you can also recollect what we did earlier. So the color I will make changing as the value of a changing. So I'll go to advanced, go to HSL, and this hue is the main color, and it depends on A, so I choose this function just like that, absolute value of A, so it will be 5 only, maximum value, and then divide by 5, and you get this one. Saturation always say to 1, the main color will be brighter, I suppose. And lightness, make it say 0.5. You experiment with that. I am not going much into the detail. Okay, so after doing this, you see this curve looks like this, and as you vary A, the color of the curve changes for different values of A. Clear? And a nice looking pattern can be created by activating the trace mode of this function. So you go there and so trace you do, and that's all, and then play this. Okay, and since it is multicolored thing, it is better you always go to a no grid, show axis, no grid, no grid, show axis, so like that. Clear already. And then show grid you remove, no grid, so it will be like this, and then you select the background color a bit darker, and that will do by going to basics, and then there is a thing here which is the background color, select it darker a bit, and then OK, and and if you play this dynamically varying waveforms will be what you will be seeing, and very nice looking curve. Okay, and so as you vary the amplitude of the function, this will go on varying. So this is about, I mean, I have really repeated what we learned last time, but with a different function. Okay, so I stop playing this and come back to our original screen. Okay, how do I do it? You clear all, I do, don't save, and it will be like this. And also you bring your axis, which is important for doing serious maths, and show grid, yes, grid is yes, and show axis I have shown. Major grid lines you show, minor grid lines. Okay, so this is the thing. Now what I am going to tell you about, after I have drawn some functions, one would like to know what the derivative of that function will be. Natural question to ask. So for example, you have a function sine of x, okay, it is drawn, then this function is created with name f with red color, and then you say you want to find out the derivative of this function. We know it is cosine x, derivative of sine x is cosine x, but nonetheless we will use this particular command. As I was telling you, the commands are very simple. In this, not only simple, it is the correct name, derivative of this function. So type derivative. Okay, something will come out, derivative. And then you say derivative of the function if. Suppose you do like that. Does it take? No, it does not take. So I have to delete this. I will write this derivative of the function. So in the braces you write f here, f, and you see your cosine x appears. So this blue function is the derivative of the sine function. Clear? So for that matter, any function you can find out its derivative. Okay, so I have chosen this function. For example, let us take another example. You say, and you hide these two functions and write, say, x square, a parabola passing through a vertex is at origin and in the upward direction in the positive half of y axis. So this is the curve, and you simply write derivative of which function? Oh, cancel. You type here derivative of what function? G. Derivative of function G. You write G. And you see the derivative of this function is 2x, and it is a straight line passing through the origin with a slope 1. You go by 1, y increases by 2, so 2x. So this is how one can find out the derivative of a function so easily. Let us take another complicated function. Let me hide these two, and the function, as I was telling you, that say 5 of sine x divided by x. Okay, and you hide this function. And also see, one thing is clear, that gx derivative we write dg dx, that is g dashed x, g prime x. So it gives automatically its name, so that you can identify whose derivative is this. Oh, function g dashed. So very logical in that sense. So here is the function hx, and the function which I just sometime before discussed about, plotted about, and this one I will write derivative of the function. What is the function? This is hx. Yes, so write the name of the function, and the derivative of the function is obtained. Clear? So derivative of this function, also it writes down its equation. This red colored curve is the derivative of this function. Clear? You derive, take the differentiation, you will land up with this, and this will be the curve. Clear? Okay, now what is derivative after all? A function is given. What do you do at a given point? What is the rate of rise of that function with respect to x? Is the derivative of the function at that particular point, isn't it? That is what I want to say. You just try to recall that any function is there and you have a function like this. So derivative at this point is nothing but you have to draw a tangent here, and the slope of this curve will, this is the tangent, tangent, and this is a point where you have to draw the tangent, and the slope of this line is the derivative of that function. Okay, and at this point it will be somewhat like this. So another point B, you can find out the slope of the function. Slope of the function is the value of the derivative at that point. Okay, GeoGebra handles this situation very efficiently in this fashion. Let us see. For example, first go to this simple fx equal to, I am so sorry, let us go to fx equal to sin x, only this curve. See, as I was telling you, to make your board clean here on the graph paper side, you select the functions with which you are working with. There are so many functions, but I have put them behind this screen without selecting them. I have not selected them, so only fx sin x. Okay. Now, what can be done is you select a point here. You select a point, any point, say any point first you select 2, 3. Okay, and the point is shown here. Now this point I will just bring it, I'm so sorry, I will just bring it suppose here, and I will put it on this graph. Now the statement of the problem is, okay, you have a graph which is sin x and you have a point. What is the name of that graph? Fx. F is the name of the graph. So you have a graph here f and a point here a. And suppose you want to find out the derivative of this sine curve, the value of the slope of the line at that point, at this point. Got the point? So there is a statement here you have to make, that is slope. So slope of what? Slope of okay, slope of what? Slope of f at the point A. Does it take? No, it has not taken. So you can just change it, slope at A of the function f. No, you write like this, tangent. Okay, this you I recollect that. Delete this. You simply write tangent. So you have to draw a tangent. Where you have to draw a tangent? At point. See, the help is forthcoming. A point. So at point A, and this point A lies on the function f. Yes, it draws a tangent at the point A. Got the point? and it is a negative slope, as you can see. As x increases, the value of y decreases, so negative slope and not only that, if you vary this point, because it is not a fixed object, you put it and you get various slopes at the different points. So here the slope will be close to 0 at the peak value. Similarly here it will be 0 and it will be a line parallel to x-axis and so on. So this is how the tangent comment can be utilized to determine the slope. Now if you want to know the exact value of the slope at that point, so I take it here. Suppose bring the point A here, the positive slope, and tan theta of this line here, that is the that will be the slope at that point. So this you write as show me the value of slope. I think it will be slope of the line. So it has created a line, y is equal to this one, and the name it has given is I, slope value. So simply write I, and it shows the value of the slope, and also it shows the tan theta. You calculate this by this at that point. Visually it is so, and the value of the slope is this one. And as you can see, if you vary it, the slope here will be close to 0. At the peak it will be 0. If you can put it, then it goes to negative, and also your slope value is depicted side by. So what is the value of the slope? Value of the slope is given a function at a particular point. You draw a tangent to the function, and what is the slope of the straight line is the value of dy dx at that point. So in this lecture I have new things I have told you about how to find out the derivative of a given function, and what is slope of a line, what is the slope derivative value at each point. So if you also sketch cosine x here, which we have shown, it is the derivative of the function. You can see as you vary here, this value is the value of the slope at that point of this curve. Okay. So that's all for today, and the functions can be easily drawn. Its derivative can be easily drawn. If you are interested to find out the slope of the function at a particular point, you can do it. Only thing, I have created a separate point, then moved that point because that point was free object. I put it on the graph paper and got the slope of this. So slope is another instruction. Slope, not slope, tangent. Tangent at a point, this instruction. Tangent at a point to the function f. So f must have been defined here, and you get this. Is that clear? So today I stop here, and we will continue in our lecture 6. Perhaps I will start with sequences, another very important concept in GeoGebra. Thank you so much for listening.